Well, good morning. This is 11:33, 3 minutes late getting started on Thursday, the 21st of November, 2019. It's supposed to be linear algebra class. The sad news is I'm the only one in the room right now, so I guess I'll go and get started, even though there's no one here to hear. But that's why I'm recording it. Hopefully some will be coming in. I think one told me he wouldn't be here today because he had a job conflict today. So let's see what we can get done. Now, my memory is that we're in Chapter 4, Vector Spaces, and Section 4.2 is also named Vector Spaces. And I think we have a student. Yes, we do. Good deal. All right. Swap out the lights. Sorry about the board. I don't know how the work studies to get in here to clean the boards. Just sitting in my office, I think, all morning, and this room was open, but I don't know. Anyway, there are 3 announcements that I know about. There are probably some others that I haven't gotten to print, or whatever. Now, this, to me, doesn't sound like anything to write home about, but it is a possibility. And I think it's from one of our coaches here at Lawson. I don't know the gentleman. His name is Jonathan Jefferson, okay? I assume he's a coach here because at the bottom he says Coach Jefferson, Lawson State Community College. So I assume this is legitimate. It's a job offer. The company name is No Kid Hungry. No Kid Hungry. The company description, No Kid Hungry is working to end child hunger in America today by ensuring that all children get the healthy food they need every day to thrive. Okay? The job title is Brand Ambassador. Now that doesn't say a whole lot for me, but I don't know if it's the brand of No Kid Hungry or what brand. But anyway, that's the job title. The job description, 2 bullets on it. Send out the items through the mail to the list of orphanage homes that would be provided to you in your city. Okay? It's a little ambiguous, but I don't know what the items are. Maybe they're promotional items. Maybe they're items that you're sending them to food items. I don't know. Number 2, mailing out letters of invitation from us to other non-governmental organizations or NGOs, foundations, or businesses in your city. So that's sort of some recruitment type stuff. Interested candidates should contact Henry via email. That sounds pretty unprofessional to me. Henry, no last name, nothing. They do give an email address, and the initials are HS, so maybe it is Henry something or another. And then there's 2, 4, 6, 7 numerical digits after the HS at gmail.com. So I assume all this is legitimate. The weekly wages, $350 a week. Now, that sounds a bit on the low side to me, but I'm not in the job market now, so I don't know. But it is a job, so that would be good. Thank you. Looking forward to hearing from you, Coach Jefferson, Lawson State Community College. So, no other information is given here. It may be a really great starting job for somebody, okay? So if you know of anyone that's looking, or just, I don't know, it may even be part-time work. I don't know. If you know of anyone, pass it on. I'll leave it up here for a while. They have no indication on how long it's open. So I don't know. Now here's one that's almost as confusing, I would say. That's not confusing, it just has some things to be desired. This is from our dean, and the subject is the Student Government Association, or SGA, Student Drive Police Support. And the only thing it says is Lawson State faculty, staff, and students, please contribute to this important SGA drive. Thank you. And here's the drive. Sponsored by the Lawson State Student Government Association and the ambassadors. It's the personal hygiene drive. All donations will be distributed to local homeless shelters. Now, the next thing it says is November 13th through 22nd. I don't know if that's when they're delivering them or if that's what the drive is. But today's the 21st, so it ends tomorrow. This was emailed to us yesterday. So they did give us a lot of time. It was in place from the 13th, but I saw it last Friday on the Birmingham campus. It's posted on the wall. Now, here's the part that really gets messed up, or at least part of it does. Donation drop-off. On the Birmingham campus, the Academic Success Building. Where that is a big old building, but I guess it's going to be pretty clear where you drop them off. On the Bessemer campus, Student Activity Recreation Center. When I brought my stuff in Tuesday, I think it was, I took it by there. It was locked up. So I thought, well, maybe they just don't have it open yet. So I went back after my first class and took it back by there. It was still locked up. So I went around to see if I could find an administrator who might know something about it. And when I did find Dr. Herndon, she said, oh, the person who was student activities on this campus is no longer here. So we don't have anyone here. And with no one here, no one unlocks it. I said, well, how can we drop off things? Oh, well, I'll take them over for you. I said, well, I'm going tomorrow anyway. I was thinking it was Thursday. It was Tuesday. So I'm going tomorrow now, so it is Thursday. Now, so I don't, as far as I know, the only place to drop it off is Dr. Herndon's office. She'll take them over. If you know of anything, I'll be glad to take them. But we've only got till tomorrow. So anyway, here is the recommended items. Shampoo, conditioner, soap, shower gel, combs, brushes, tampons and pads, lotions, deodorant, baby wipes, hand sanitizer, and socks. Now, they have a picture here of toothbrush and toothpaste, so I also found the unopened thing of toothpaste at the house, so I brought that too. So I think they'll take them, but that was just suggested things. So anyway, as far as I know, the deadline for that is tomorrow, but they may take it later too. I emailed back to Dean and said, look, that place is locked up. There's no place that I know of to deliver it here. All right, then. This came in the mail today. The subject is a 2020 summer research experiences for undergraduates. Now, they have these all over the country, okay? A lot of the major research universities will sponsor these. This is from UAB. And it says, we're now recruiting our National Science Foundation, NSF, supported research for experiences for undergraduates, that's REU program, that's going to run from May 17th to July 24th, just a little over 2 months, 2020, in experimental and computational materials research. Our program is among the longest running NSF REU programs in the country. We offer a broad range of interdisciplinary materials research experiences to undergraduate students with diverse backgrounds in physics, chemistry, applied mathematics, and engineering. Now later you'll hear other fields could be included here, I think. The research projects include, but are not limited to, electronic materials. So electronics seems like nanomaterials, lasers and optical materials, biosensors, biophysics and biomaterials, and computer modeling. So it sounds like computer majors would be quite good at this too. Okay, the scientific research projects are developed specifically for undergraduates by an interdisciplinary team consisting of science and engineering faculty at UAB. Please find enclosed a recruitment poster. I had it up in here, but then it says on here to put it in a, how did they say it, high traffic area. I thought this isn't that high traffic, so I took it down to the career services person. They will put it up on the bulletin board, I hope. If not, I'll bring it back up here. Find a enclosed recruitment poster for display in high traffic and accessible areas. Also note that the application can be submitted electronically via their website, and they give the website. The application deadline is not until March 15, 2020, but it's a good idea to get started early, especially before the holidays, when you have plenty of time to work on it. Decisions will be made no later than 15th of April, tax day. We would appreciate it if you would bring the summer research opportunity to the attention of qualified undergraduates like you at your institution. We are especially interested in receiving applications from qualified women and underrepresented minority candidates. Okay? They accept it from everybody, but they are really looking for students in those areas specifically. If students have any questions about logistics, housing, and travel arrangements, they can contact Sharita Cadenhead, our program coordinator. The phone number, email, or listen. Thanks for your assistance, and please display the poster. Okay. Is that good? Where to apply? I think you go to the website, and I think it's all done online. It says here, also note that the application can be submitted electronically via our website. Well, they don't say any other way to do it, except that. So, but I guess you could go to UAB and apply in person. I don't know, but obviously you can do it there. So if you want the website address, or if you know someone who may be interested in it, it's a good program. And I know we've had students, pretty sure we've had students from Lawson participate in UAB's REUs before. Maybe not this one, but perhaps this one as well.
I think I'd be interested in it just because, all the other ones, they are the state, not
Right.
state, in-state.
Right.
So if I could possibly stay in-state, that would be nice.
Yeah. Now, let me tell you about these. I don't know if you noticed the statement in there. If students have any questions about logistics, housing, and travel arrangements, usually what's included in these things are housing for those 8 weeks, 9 weeks, whatever it is. This one sounds like more like a 9 or 10 week. Quite often with the housing comes a food plan, okay? And almost universally, the ones I've seen, they reimburse travel or pay for the travel. I mean, they pay for the travel one way or another, either providing the tickets for you or you getting them and then do it. So don't let that stop you from doing one of the out-of-states if it's really in an area of your interest. But I understand you may not want to be out of state and then have no transportation to go anywhere and maybe stuck on campus during the weekend when you'd rather be at home or something. So I understand that, but understand they do quite often pay for everything. I mean, everything.
I also think, even though I want to focus on what I prefer,
Right.
like astrophysics related research.
Right.
Materials science is pretty cool too, because UAB is real big on that. Like that's pretty much what I guess I want to say 100% of the faculty, the physics staff did that was in materials research. And the stuff that they talked about was pretty cool, like superconductivity and a lab that I was about to work in. It was something to do with superconductivity, if I'm not mistaken. But it was basically like I didn't get to like the nitty gritty because I had to leave before I could actually start. But like what they was gonna have me doing, I was gonna basically be growing diamonds.
Yeah.
Like a circuit or something.
Yeah.
I can't remember the reason why, but the concept was cool. Like
Yeah.
they think they it was like they heated up a methane gas and then they ionized
Right.
into a plasma or something like that.
Right.
And then
you may find that some of these do coalesce when you're saying astrophysics, when they talk about things such as, and it's not limited to, electronic materials. I don't know that could have something with it. Nanomaterials could easily move in that direction. Lasers and optical materials, that, it could easily be going that way. The biophysics possibly, but then they mention biomaterials, and then somewhere else they say interdisciplinary materials research experiences. That could be materials that you might use in zero gravity, or materials you might use in spacecraft or space. So just because it doesn't say it, it may be connected, because when they do say, physics is mentioned here several times, and in fact, this came from the Department of Physics. The professor here is, I assume, in the Department of Physics. In fact, I'm trying to remember, I may have actually met this one. Did you say something about growing diamonds?
Yeah, that's Dr. Bohr.
Vohra, V-O-H-R-A?
Yeah.
Yeah, that's him. That's who it is.
Yeah,
So he's involved with this. So
he don't even know what happened to me. It was just I just kind of disappeared. But we was working on because they had to buy a new microwave. It was basically the device that ionized gas.
yeah,
And they had bought a new one, and because it was higher powered than the last one, they had to buy a new cooling system as well. So we was in the process hooking those tubes up, a new cooler to the water supply and stuff, and getting the microwave installed, and then hooking it back up to the computer. Just basically we was resetting the lab because it was getting quicker. So I didn't actually get to start doing anything yet, but I was in the process of getting to do that because he was working on my offer and stuff, me to get paid and all that stuff. But because of what happened, I wasn't able to stay. So that's kind of left. My eventually he just wondering what happened. You was just here while you left.
I think that may be the same guy, because literally 20-some years ago, I needed to take a few more graduate level physics classes to be able to teach physics here. So he was my contact person, and I remember, he was working in growing diamonds and things like that back then. I think he was just getting the program started, so I knew he was an Indian, and that sounds like an Indian name, and it may actually be him. Of course, he was fairly young back then. He may be a little older now. So
He don't look that old.
he does. The Indians keep their age pretty well. So, but anyway, I bet you it's the same guy. So yeah, this isn't going to be far-fetched from what you're interested in, probably. So anyway, that was probably enough of that. Now any questions on anything we've done so far? All right, I think I'm going to have to do these aren't really cough drops. They're actually they call them ginger candy, but they are way more ginger than they're candy. They are very strong, and it really helps, or at least I imagine it helps my throat. I think also calms the cough a little bit. They certainly increase they're doing some work in the building. That's what the strange noise is. They're having to cut a hole for a bit. Okay. Before you came in, I was saying we're in Chapter 4, Vector Spaces. In Section 4.2 is also named Vector Spaces. And we talked about the 10 criteria that have to be met, axioms they call them, for a set to be called a vector space. And we went through those last time, and basically we showed that R2 and Rn were both vector spaces because they, in the previous section, specifically they listed those 10 things that they met. Here, though, is a very different one. It says, show that the set of all 2x3 matrices, let me get my pen set out. The set of all 2x3 matrices. Okay? All 2x3 matrices. That means all matrices that are goodness gracious, 2 rows by 3 columns. All matrices, every matrix you could do that would be a 2x3 matrix. You could put any number in the world in there. Biggest numbers, smallest numbers, negative numbers, irrational numbers, complex, not complex, we're going to stay in real numbers, I think. Positive, negative, doesn't matter. Put them in there. So there's a set of all 2x3 matrices with operations of matrix and addition and scalar multiplication as normal, which means if you have any 2 matrices, let's call them M1 and M2, when you add them together, they form a 2x3. That space is closed under addition. Also, when you multiply some constant by it, that'll give you a 2x3 matrix, so that's closed. I think I recognize you from somewhere. Good to see you.
Complicated situation. I thought I was going to get moved to a different work schedule this semester. Unfortunately, it's not until next semester.
Oh, really?
Change over. So I'm basically going to take off to come here.
Okay.
More or less, all you can do is pick up the test and watch the stuff at home.
Okay. Did you get any of the tests?
I had one. Unfortunately, that notebook is gone.
Okay.
I do still have a lot of my stuff written down at home, though, for
Okay.
this one. So I should be able to fill that out pretty quickly.
Okay. I have a copy of test 2 here. It's not stapled, but you say you don't have test 1 anymore? Okay. I'm going to have to make another copy of test 1 because what happened, my work study student decided to shred them.
Oh, no.
Oh, yeah. So that says test 2, and this one says test 2, but this is test 3.
I'll go ahead and mark on it.
Okay?
Thank you very much.
And I think you must have destroyed test,
One.
no, test 4 as well, because it's not in my stack.
Okay.
And,
I guess I'll be in your office.
What's that?
I've got a class much later today.
right,
If you're still there in your office, so I guess I'll meet up.
okay. I will be here till 8 o'clock tonight.
I will too. I have
Okay.
class at 7 tonight. So
Okay.
Sometime between
Are you going to be here through this class, or you got to go?
I'll be here through this class.
Okay. After the class, can you pick it up then? Okay. I'll have to go run off another copy because, and I mean, not only did she destroy the master, she destroyed all copies I had of it, and she destroyed the key I had for it. And there was absolutely no reason for any of that, but
This is
she
what
just,
scanners make copies of these things.
So-
Before we destroy the physical copies.
yeah. So anyway,
Thank
we're
you.
on,
Thank you very much. Though.
all right, we're in vector spaces, chapter 4, in 4.2, which is example, also called vector spaces. And we're just talking about, here we have a set of all 2x3 matrices. Now, if the first thing out of your brain says, wait a minute, I thought you were talking about vector spaces. This is a matrix. Well, what's that?
You represent a vector as a matrix in 3 dimensions, right?
Well, yeah, and the thing is, in our term vector here, it's no longer just a directed line segment. Anything that fits these descriptions can be a vector. Functions,
So it doesn't have to be 3-dimensional.
it doesn't have to be a 3 or 17-dimensional thing. It can be anything that fits these criteria. The first criteria is if you have any two 3x3 matrices, add them together, you're going to get a 3x3 matrix. So that is closed under vector addition, matrix addition, but now we're considering those as our vectors.
I always
Or, yeah.
thought that the vector matrix addition rule did look a lot like the vector.
Absolutely, it does. And the second is likened to it. If you multiply any scalar by a 2x3 matrix, you're still going to get a 2x3 matrix. So scalar multiplication is closed. So those are two criteria. Okay? The 10 criteria that are listed on the previous page, page 155, if you've got a copy of the book, the first one is closed under addition. It is. If you add any two matrices, M1 plus M2, 2x3 matrices, but then you also add M2 plus M1, you get the same result because they're commutative. So, absolutely. They're associative. If you had 3 2x3 matrices and you add the first two and then add the third, then you get the same thing if you added the first one to the sum of the second and third. So, matrix addition is closed under, follows the associative property. There is a zero vector, because remember, any 2x3 matrix could have all zeros in them. And if you do, that's your zero matrix. And it follows all the properties of its additive identity element. Add it to any other matrix, and you get the same matrix. Okay? For every 2x3 matrix in this space, there is a vector that you could say is the opposite of that. So if this one was, for lack of anything else, I'll make it as simple as possible, or not as simple as possible, a simple one. 1, 2, 3, 4, 5, 6. The opposite of that would be -1, -2, -3, -4, -5, -6. So any matrix you happen to do there, just negate every term, and you've got its opposite, and that would be called the additive inverse of that matrix. That must be existent for it to be a vector space. Okay? So those are the 5 that deal with vector addition. Scalar multiplication, we've already said, C times a 2x3 matrix is going to be a 2x3 matrix. And that obviously is in the space, because all 2x3 matrices are in the space. Also, if you were to do C times the sum of two matrices, M1 plus M2, that's the same as C times M1 plus C times M2. Yeah, matrix. It's sort of a distributive property of scalar addition over, and I'm saying scalar multiplication over matrix addition. And then, if you have two scalars, C plus D, multiply that by any matrix M, that's the same as C times M plus D times M. Another distributive thing, this time is scalar multiplication over scalar addition. Okay? Seems strange, but that's what it is. And then the one associative situation you could have, C times DM, and we call them M now, would be the same as CD times M. And that works too. That's distributing two scalars with one vector or matrix. And then there is, if you multiply the number 1 times any 2x3 matrix, you're going to get the same 2x3 matrix. So all 10 of the criteria or axioms are met. So sure enough, this is a vector space. So what we just described is actually a vector space. Even though it doesn't have a vector in it, it has 2x3 matrices in it. Now, if that wasn't weird enough, and I guess not weird, but what if you're considering all polynomials of degree 2 or less? All polynomials of degree 2 or less. Let P2 be the set of all polynomials of the form P of x is equal to a sub 2 x squared plus a sub 1 times x plus a 0. That's a polynomial of degree 2. Okay? Where a1 or a0, a1, and a2 are any real numbers. Okay. Okay. Now, let's think. Always you have to sort of define or accept what your standard linear operations are going to be, and that's vector addition and scalar multiplication. So if we consider this, the sum of the two polynomials, so you had a P1 and a P2, now they're both, wait a minute, we probably shouldn't use that. What they do is P and Q, okay? The reason not, they just said P2 was a set of polynomials 2 or less. If I said a P1, then you would assume that's a polynomial of degree 1 or less. That's what I meant by that. So let's call this P and Q, okay? You can't list them all, but you can list those two, okay? P and Q. They're both in the set, okay? Well, if you add these two polynomials together, you're going to get a, let's call it R, which is a polynomial that's going to be degree 2 or less, okay? Because adding two polynomials cannot raise the power, okay? And since it can't change the power in any way whatsoever, so these will be two polynomials of degree 2 or less. So that's your definition for the sum. And also, if you were to multiply C times one of those vectors P, you'll also get something, let's call this Q. Let's call it S, maybe that would be for some. That's going to be a polynomial of degree 2 or less. Because if that C is a constant, no variables at all, can't have, it's a constant. You can't up the variables, you can't make it a fractional form, there's no way. If that P is a polynomial, multiplied C by is still going to be a polynomial of degree 2 or less. So they actually, for some reason this time, spell them out. So let's actually spell them out. This would be, what do they call it? They call A the coefficients of PA. So let's do that. A2x squared plus A1x plus A0. That's your P, just like up here, okay? Then add to that the Q, not Q. This one they're going to call the coefficients B's, okay? That'll be B sub 2 x squared plus B1x plus B0. And if you add those together, you add by like terms, so you get A2 plus B2 times x squared plus A1 plus B1 x plus A0 plus B0. Okay? That's a polynomial of degree 2 or less. Because A and B's are just numbers. They're just real numbers. Yeah, that is a 2. It's a really ugly 2, but it's a 2. That next one's a pretty ugly 1, too. Okay. Now this would be C times A2 x squared plus A1x plus A0, and that would be, whichever order you wanted to, CA2x squared plus CA1x plus CA0. Okay, guess what? That's the polynomial in degree 2 or less. This is just a different constant. That's a different constant. That's a different constant, but they're still constants. All real numbers. So C's a real number and your A's and B's are real numbers. Okay. Now, does it meet all the 10 axioms, they call them here? Well, the first one is, we've already said, the sum is also a degree polynomial of 2 or less, so it's closed. It's commutative. It doesn't matter what order you add those two polynomials, you're going to get the same result because addition of those real numbers is commutative as well. If you had 3 of them and you associate them, add these two together, add that one, or add this one to the sum of those two. Guess what? You're going to get the same result, okay? And it will always be a polynomial of degree 2 or less, okay? There is a 0 polynomial. That would be with A1 equals 0, A2 equals 0, A0 equals 0. All the coefficients 0, that would be your 0 polynomial. Just the polynomial 0. Add it to any other polynomial, like A2x squared. Add that, the 0 polynomial to it, you still get the P polynomial there, okay? And for every polynomial, A2x squared plus A1x plus A0, there is another one that's the opposite of that. Minus A2x squared, minus A1x, minus A0, you add them together, you get the 0 polynomial, okay? So, all the addition parts work, scalar multiplication part work. C times any 2-degree polynomial or less is going to be a 2-degree polynomial or less. It's closed under scalar multiplication. You can also do the same thing we did before. Multiply C times the sum. There's a sum right up there. Multiply C times that, and that would be the same as C times P plus C times Q. Okay? It works out that way because the coefficients are real numbers and they follow those same rules. Okay? The next one is that sort of a distributive one. If you add 2 constants, C plus D, times any of those polynomials, you're going to wind up with a polynomial that's equivalent to C times the polynomial plus D times the polynomial. That's distributive rule. The other one that's sort of like it is C plus D times one of those polynomials will then be C times that polynomial plus D times that polynomial. That's number 8. Number 9, the one way you can do associative property of multiplication is A times BP, where P is a polynomial. Well, BP would be a polynomial, and A times that would be, C times that would be a polynomial. And that's the same as CD times that original polynomial. Sure enough, it works out exactly the same. And there is a number 1 that you multiply by any polynomial, P, and you still get the same polynomial, P. So indeed, set of all polynomials degree 2 or less is a vector space. Okay. And they show a couple of those proofs there. All right. Now, stepping that one up a notch, I don't don't know if I'm going to need that. I'll just do it here. P sub n, now these are capital P's here, little p's and q's there, but this is capital P n. That should have been a capital P sub 2, okay? P sub n is defined as a set of all polynomials of degree n or less. Okay, less than or equal to n. Together with the zero polynomial, okay, the procedure used to verify that that is a vector space as well can be extended to show that P sub n with the usual operations of polynomial addition and scalar multiplication is also a vector space. That's also a vector space. All right. Now, example 5. Let's clear the screen. And here's another U set. This set we're naming capital C, and it's defined from minus infinity to infinity. Okay? What this stands for is a set of all, I wanted to just do a parentheses on it, but I was afraid it might get confusing. Okay? It's a set of all real value continuous functions that's the only place I can see they get the C from, continuous functions. Seems like they should have called it capital F, all, but they're saying all real valued continuous functions. No what do they call that when they divide when they define several points of the domain, but you could have a jump here and then a jump over here. Piecewise defined functions that are not continuous, okay? Set of all real value continuous functions defined on the real number line. Okay. Okay. Now this function, since it's all real value continuous functions, hey, guess what? We're just doing polynomial functions. Polynomial functions are by definition always smooth and continuous. This includes continuous functions that aren't smooth, like absolute valued functions. Not a polynomial that doesn't have smooth characteristics. It has a point, a corner on it. Polynomial functions don't. They're always smooth and curved. This is any continuous function. This could include your sine and cosine function. Okay? Doesn't have to be polynomial function. Could not include tangent, cotangent, secant or cosecant, because they have vertical asymptotes, discontinuities. Okay? Exponential functions are not polynomials. They would be included. Log functions are, whoa. Log functions wouldn't be this one because this is all ones that are defined from negative infinity to positive infinity. All exponential functions are defined there. Logs are not. They only start to the right of 0. They don't even count 0. Everything greater than 0. Okay? So they can't do that with them. Okay. Now, For instance, and they mention f of x equals sine x, g of x equals e to the x are all members of that set. Now, addition of these would be defined this way. If f and g are both continuous functions of the real number line, then f plus g, f of x plus g of x, would have to equal I can't talk. Goodness, I can't even read my writing either. Let me see if I can make that a little bit better. Okay. Because as I get to talking and don't pay attention to what I'm writing, it gets all run together. You have any two real value continuous functions, we'll call them f and g, both of them are x, f of x and g of x. Okay? Now, remember, everything has to meet those two linear criteria. That if you got f and g, the f plus g is also needs to be a real value continuous function. Well, guess what? Adding two functions that are smooth and, well, don't have to be smooth, real and continuous, adding them together, you're going to get something that's real and continuous. So it's closed under addition. Also, if you multiply a scalar c times either one of those, you're going to get a real value function, continuous function. Multiplying by a c does not negate or eliminate the reality of that function. Even if c was negative, all it does is negate the function. It doesn't make it discontinuous. Okay. All right. Now, the next rule you have to do, vector or function addition, multiplying by a scalar constant. Well, that's still going to give you a continuous function that's that's defined everywhere. Okay? If your original was, this will be. All right. All right, it says show that this set of continuous functions, all real value continuous functions defined on the real number line, to show that it is vector space. Let's go through them quickly. Certainly, they're closed. The sum of any two continuous functions is a continuous function, so it's closed in vector addition, you might say. If you add any two continuous functions together, and then reverse the order, you're going to get the same result. They're they're commutative. They're associative. It doesn't matter how you just if you add one to the sum of two others, or add the first two, and then add the third, any two continuous functions, they're going to still be continuous functions, and it'll be the same function no matter how you add them. They're associative under addition. This set does contain the zero vector. You know, it has to. If it does have a zero, it can't be a vector space. Well, function f could be 0. That's a function. Okay, it's continuous, just a horizontal line on the zero axis, on the x-axis. That is a function in this space, in this set of things. And when you add it to any other function, you get just that function, because it doesn't change anything. And for every function in your space, I'm having trouble breathing, sorry. There is a vector in V that you could denote by the negative of that. So let's say f of x, whatever terms are in that function, whatever description of it you have, sine x, e to the x, whatever it is, you can just negate it, and then when you add those two functions together, you'll get the zero function, because every term, term by term, will add the zero. All right? That's the addition part, the scalar multiple part. We've already sort of mentioned, multiply c times a function, you still got a continuous function, okay? Multiply c does not create a deviation from that space, okay? The scalar multiple rules, you don't multiply. Also that sort of distributive property, c times the sum of two functions, just like c times the sum of c times a function is a function, c times the sum of two functions is a function in that space. Always still continuous, okay? And what's more, it would be the same as c times f plus c times g, because that's how functions multiply and add, by these rules, okay? And then sort of the other distributive that they show, if you had two real numbers, c plus d, multiplied by a function f, it's still a continuous function, and you could make it c times f plus d times f. Yeah, they multiply and add the same manner as real numbers, because those coefficients are real numbers. And the one associative is c times, let me do it, d times the c of f is going to be the same as cd times f, because they're still continuous functions and that'll work. So, and over the last one, 1 times a continuous function is still that same function. So it has a multiplicative identity element. So, not only are vectors in Rn, any n, any given size matrix, all those matrices of that given size, that creates a vector space. All polynomials of degree 2 or less, frankly, you could do n or less, okay? You don't have to be 2, okay? But they all have to be n or less, okay? And then all continuous functions defined on the entire real number line, they are also vector spaces. So, they do a summary of what they call important vector spaces. Okay. Oh man, my head. R, that's the set of all real numbers. Okay? And that also would be R1. R2, the set of all objects on a plane. R3, the set of all objects in space. Okay? Carry that as many R's as you want to. I can't wave my arms and show them to you. R to n. Because now you have n dimensions that I can't visualize with 3. Okay? Kind of can imagine maybe 4. Kind of, but not really. And you could do anything n. Okay? Here's your continuous functions. C from negative infinity to infinity. Okay? Now here's one we didn't do, but they're saying it's an importance vector space. C, continuous functions on a set, closed set, from A to B. Okay. Continuous functions defined on the closed interval A to B. Okay. But it'd be a set of all continuous functions defined on that closed interval. Okay. Now that you might need to puzzle about a little bit, but you can. Now, I said you could have piece of 2, piece of 3, piece of 4, piece of n. They say P the set of all polynomials. My word. There's an infinite number of degrees they can have. So infinite number of polynomials within any degree. So yeah, the set of all polynomials certainly will work. And the set of all polynomials of degree n or less will work. That's the one we were doing, p sub n. Then that would be degree n less than or equal to n. Okay, so up to some given degree. Those are vector spaces. Now, matrices, now they do m comma n, which is fine. I don't see why they don't do m times n, because that's what they're going to say. Set of all matrices that are m by n matrices. So I wrote it wrong. M by n. And if that's true, then certainly all square matrices in n, which would be n, I can't write again, n by n matrices, all square matrices would be vector spaces. Now, most of the time, if something's going to sneak up and bite you, to keep it from being a vector space, quite often it's going to be the fact that it doesn't have a zero in it. Everything we've listed here can. All functions can have a zero function. Polynomial functions can have zero functions. Because remember, this is degree n or less, so it can be degree zero. But a constant is degree zero too, but a constant zero is also degree zero. All polynomials, of course, would include the zero polynomial. Any matrix, square or rectangular, if all the elements are zero, then you got it. So that's usually the one that might be most likely to keep it from being a vector space. Okay. Let's, I'm so sorry. I need to quit talking, but I don't know how to do that. So I don't want to do another cough thing now. We're not got that much time left. Let's look at theorem 4.4. Properties of scalar multiplication. I thought we had already sort of hit these, but I guess they want to re-emphasize them. Let V, now I'm still going to draw it as if it's a vector, okay? Just understand it doesn't have to be a vector when we're talking about vector spaces. But they bold them in the book, which is the same that I represent it by an arrow over it, because I don't write bold. So let VV, any element okay, of a vector space now from now on, I'm going to try to do it. If I'm writing vector space, I'm just going to put VS. That's going to stand for vector space. Now, their name for it is just always capital V. Okay? Doesn't have to be, but that's what they use most of the time. If you add more than one of them, they'll give a different letter for them. And let C be a scalar. When you say scalar, any real number. Okay? We're not dealing with complex, with imaginary parts now, just real numbers. Then the following properties are true. Okay? Okay. First, 0, the number 0, times V, that's any element of that vector space, whatever vector space it happens to be, is going to produce your 0 vector. Now remember, that doesn't have to be a vector. It could be a matrix, it could be a polynomial, it could be, just a whole bunch of different things. Okay? Number 2, C, any real number, multiplied by that vector, which is any element of a vector space, is equal to the 0 vector of that vector space. Okay? If that was a matrix, a 7 by 3 matrix, then that would be the 7 by 3 matrix with every element being 0. So I identified that with the arrow just as if it's a vector, but remember that's just a vector space, element of a vector space. Number 3, if, here's a conditional one, if CV is equal to 0, then you have only 2 options here, folks. Either C is equal to the scalar number 0, or V, the vector element, the element of that vector space, is your 0 element of that vector space. It's the only way for a product of a scalar times an element in a vector space to be the 0 of that vector space. That has to be the vector 0 too. Yeah, sorry. Or the vector V has to be. So one of those others is true. And then number 4, and this is one that seems like we've already said, -1 times any element of that vector space is going to be the opposite element of that vector space. And that's called the additive identity. Okay? This could be called the 0 product principle. It was with real numbers, with polynomials, with factors, with anything like that. It is with vector spaces as well. And they do a little proof here of number 2, which is it's almost seems so incredibly trivial. You think, why in the world would you ever write it down? But anyway, read through those, make sure you follow them. Okay. They have another application of linear algebra, and this is basically Hooke's law when you're dealing with one-dimensional space, one-dimensional motion. Okay? And you can read that to your heart's content. Now, everything we've been talking about is a vector space, and you might get it in your mind, well, then just right, anything could be a vector space, couldn't it? Well, there's some sets that are not vector spaces. We're going to look at a few of those now. We may not get them all hit, but let's just do a few of them. What if we have the set of all integers with standard operations? Okay. Now, what does that mean? You can add them together and you're going to have an integer. That's true. You can multiply them by, whoa, you can't multiply any integer by any real number and still get an integer. So no, that will not be closed under your rules for vector spaces. Remember, if you're set, you've got to be able to do your standard operations. And adding and subtracting, yeah, you still get integers, okay? But when you go to multiplying by a real number, C, you're going to get a real number C, not necessarily an integer. So the simple example of that is 1/2 times any integer is going to be, well, let's just use the integer 1 is going to be 1/2, and that's not an integer. So that set is not closed under scalar multiplication. Now, scalar could be any real number, so the set of all integers, not a vector space. Maybe other regions as well, but that one certainly wouldn't be. Okay? Now, here's one that sounds like one we've already done, but it's not quite the same. Okay? The set of all second-degree polynomials. Okay. Now, we said the set of all polynomials degree 2 or less is a vector space, but what about the set of all polynomials of degree 2? Is that a vector space? Okay? Now, the first one that comes to mind is if you multiply this by any constant c, just like the last one we did, are you going to get a polynomial of degree 2? Well, it is for any number you add except 0. If you multiply 0 times any p2, you're going to get 0, which is not a p2. Okay? So that's why you have to say degree 2 or less, or n or less, or something like that. You can't say all that. Now, that's a real simple one. That's not necessarily going to do. Here's another. If you had p of x, this is the one they give in the book, is equal to x squared. Q of x, that's a polynomial of degree 2. Q of x is equal to minus x squared plus x plus 1. Good old polynomial of degree 2. How about adding those together? Will that be a polynomial of degree 2? Well, you get x plus 1. Well, that's not a polynomial of degree 2. It is not. It is not in that set, okay? Because it's degree 1. That's why you have to say degree 2 or less, okay? So, their vector addition is not closed to that space. So both of those examples showed times when you were not closed under your, closure was your problem, okay? Let's do one that closure is not a problem, okay? Closure is usually pretty simple to spot. Sometimes it's so obvious you don't think of it, but it is there. Okay, I think this is number 8. Let V equal R2. Set of all ordered pairs of real numbers in the plane. With the standard operation of addition, so the addition of any two vectors, just like we've always said, but this time they're going to do a non-standard definition of scalar multiplication. Non-standard definition for a scalar multiplication. This seems totally weird to me, because it seems like who would ever do this, okay? Here's what this non-standard definition of scalar multiplication is. C, there's your scalar, times this vector, x1, y, x1, x2, we're going to say that is C of x1, 0. Okay? That's just how we're going to define scalar multiplication. Not the standard. Standard would be C of x1, x2, be cx1, cx2. But we're going to say, no, we're going to use this one. Okay? Now, is that a vector space? Your definition for vector addition is going to be the same. And remember, these are everything in R2. So will that work? All right. Now, This is such a weird problem, a weird setup, that your explanation gets pretty weird feeling too. If you were to pick a number, any scalar, they choose the scalar 2. It could be any scalar. And then pick any point in R2. And they just happen to choose 3, 4. That's the point in R2. Okay? By their scalar multiplication, this would produce the number 6, 0. Because that's what we said you do. You multiply the scalar by the first one, but then count the second. Whatever it is, it becomes a 0. Okay? Now, I mean, it just seems so crazy. If you go back and look at your definition, okay. The only one that fails of all those, believe it or not, it's close under vector addition, it's commutative, it's associative, there's a 0 vector there, that's fine, okay? The additive inverse works, close under scalar multiplication, those two strange little distributive rules work, the one sort of strange associative rule works, and number 10 is where you fail. Because number 10 says that 1 times u is equal to u. That's the scalar identity. But if you did 1 times 3, 4, you get 3, 0. By that strange little rule that we put for scalar multiplication. And 3, 0 is not equal to 3, 4. So everything worked. Everything worked except that last one, number 10. And my question is, why would you even come up with something so bizarre as that in the first place? So the only thing I can see that you need to learn from that, if you're going to make up a new definition of either addition or multiplication, those are the two that have to match. If you have something that's not ordinary, make sure it works for all 10 before you adopt it, okay? And that finishes right in the nickel dime of 4.2. You can do any of the odds 1 through 5, they're all at calcchat.com. Any of the odds 7 through 11, they're all at calcchat. Any of the odds 13 to 33, they're all at calcchat. Do 35, it's at calcchat. 37 is a proof. I don't know if it's all at calcchat, but if it is, you can go through that. 39, I'd say any of the odds 39 through, and by the way, 41 is a lot like the applied problem that, or example they showed. 39 to 43, they should all be at calcchat. There's a true false at 45, it should be at calcchat. There's a couple more, one more proof, 47, if you want to try that, it should be at calcchat. We'll begin next time with 4.3. Sorry we ran out today. And I sure hope by next, well, okay. You do understand there is no next week, okay? School is closed, well, the college isn't closed next Monday, Tuesday, and Wednesday. We're still here. It's just that no classes Monday, Tuesday, and Wednesday. Y'all get the week off, we don't. So if you have any business to do with the college, you can do it Monday or Tuesday for sure. And I would say even Wednesday morning. But I would not bank on finding too many places open Wednesday afternoon. There may be some. They may not let us go early, but quite often they do. So I wouldn't postpone anything that can be done by Wednesday morning. Don't wait till Wednesday afternoon. You may not be able to get it done. So there's that. So we'll be back on the Tuesday after Thanksgiving, and that's where we'll pick up with 4.3. And we'll go from there.
Set of what? Invertible determinants is not a vector space.
The set of invertible determinants, is that what you're saying? Invertible matrices.
Well,
You can invert a matrix.
I'm saying like, okay, if it's a invariant matrix, and it's invertible, then its determinant can't be zero. So if you have a set of only
Invertible matrices.
yeah, well, the invertible determinants of invertible matrices.
Right.
If you have a set of those, it's not a vector space. Right?
Yeah, okay, that's an interesting way to put it, but yeah, it would not be, because the determinants of all invertible matrices are any real number, except 0, because 0 would be, if the determinant was 0, it would not be invertible. But then you wouldn't have a 0 vector. You know, there's not a determinant 0, because that would be, so that is an interesting, I've never heard it expressed that way. That's an interesting set. No.
I was just thinking about it. I was thinking about the 0 thing.
Yeah, that 0 thing is the thing that gets you. And quite often that will be the one. Though that one example we had is the multiplicative inverse, which seems so simple, but that weird thing they set up there wouldn't work. Well, we did go over